So we have now, as usual, a little bit of time for general discussion. These talks all were very anomalous in the sense that they were very different from each other. So we have a few points to bring in, and people can be more imaginative in asking questions related to these to all the people who spoke or the participants. The audience can also participate. So what we have is that how do we effectively utilize machine learning for time domain science? We have been talking a little bit about that. How can we best craft synthetic data sets to train models? So that's one of the questions. Again, coverage. If Roman alert started tomorrow, what would fail in your pipeline within the first week? I think that's something that we can try to keep in mind. And then what is one assumption in your method that you are worried about? Forget about other people. So something to think about. And there are a few more here. 5.5 years from now, when the nominal Roman will end, what will we laugh at in today's ML anomalies world, for instance, things related to that. So it's open. Questions, comments? Yes, go ahead.
Okay. I think with classification anomaly detection light curve projects I'm participating in right now, the most thing I'm worried about is data sets. So for classification and real objects, it's labels, so curated labels. We tried to approach this problem 2 weeks ago, today Beige workshop, but still. And for simulated, it's do we simulate uncertainties, right? Could we simulate outlier detections because of photometric pipeline problems and stuff like that?
Any comments on that? Yes.
Maybe I'll piggyback on the uncertainty for classification. I think this is an important topic, but something that we haven't solved, whether it's algorithmically or by community. There are some uncertainty classification methods like Bayesian neural networks, or if you try to jackknife the training sets and try to see some changes. But it's not something that we have still a solution. So I think this may be something that we as a community could think about more.
Absolutely. So that's one of the points that keeps coming up. So one Sid mentioned, for instance, in terms of light curves as well as SCDs. So doing a joint analysis of that to understand uncertainties, but also across surveys going from optical to infrared and to the different depths which we are going to encounter for the first time. So it's going to be critical. And if we can collectively spend time on that and see how each of our method is approaching that direction in some way would be useful. Go ahead, Guy.
So maybe a year ago or 2 years ago, we published a paper on uncertainty classification for light curves. And it's quite simple to do it. If you want to do the uncertainty on the output of the neural network. So if you want, for example, to calculate the uncertainty on the probability of being such or such class, there's something super simple that you can use, which is called dropout. I don't remember. MC dropout. Yeah, Monte Carlo dropout. It's super simple to apply it. And it's much simpler than a Bayesian neural network.
I will continue this one because it's true that this method exists and it's very easy to apply, but how to calibrate those uncertainties is not trivial, because how do you define what is a properly computed uncertainty in a classification problem? Like regression, we can do it with quantiles of the distributions, but classification is not trivial. So there are some metrics on out of distribution candidates or entropy, etc. But what I have seen in literature is that sometimes these metrics work and sometimes they don't. So I don't think it's a question about the method or how hard it's to apply it. Is how do we define what a true classification uncertainty is, I think.
Yeah, and also defining how the anomalies are. So Felipe, then Jacob, and then Clesio.
I think that from the technical perspective, it is simple because the computer science people have done a lot of research in uncertainty quantification for deep learning. But I think that in our science applications, we need to first learn how to disentangle the different types of uncertainties that we have in our data before we try to calibrate them. So one obvious disentanglement that we should be able to do is separating what is your aleatoric from your epistemic uncertainty. understand what is the fundamental irreducible uncertainty coming from your data and how that propagates to your model versus the uncertainty in the model itself. And I've never seen anybody doing that.
I think I'm going to need to send you the paper because we discuss all this in the paper. So we measure both uncertainties, different ways of the quality of the uncertainty.
Okay, good coffee time conversation. Let's also move on. We don't have too much time, but we should continue this.
I think also the question that we can discuss these things, but the question is how do we communicate that to users? That's a question I have now, and that I would try to highlight there. That we might know how crappy some things are, but we still want to communicate the results. So it would be very good to have some very simple metric, maybe like just an integer number that one could agree, and that one could communicate roughly what sort of training set is this based on, how certain would one have it, something that we could really and it doesn't need to be perfect, but just something so that the users know, is this a score I should put any sort of faith in, or is it just a number that was produced?
Yeah, so in ZTF, we have been doing the binary classifiers all along. So not do one single classification, but have a large number of classifiers, each telling whether it belongs to this class or not. And carrying these multiple probabilities is a useful thing. In the game Zarth that we have, for instance, we have 2 wild classes that we put in. In case you don't know, by the way, this is Pokemon for astronomy. Check it out, Zarth. But yes, that's important, communicating, because you may know something, but being able to do that. Klesha.
Most of my comments, Felipe already did. So sorry, I haven't checked your paper, but about the error bars. But yes, Monte Carlo, Dropout, and similar ones are not the true uncertainty in the sense that we are looking for, right? Because they are uncertainties about the model itself. So the meaning of the uncertainties is sometimes an open question, depending of your choices. And whatever you do, as my colleague just said, you need to be clearly communicated to your community. Otherwise, it's very misguiding. I've seen some Kilanova candidate classifiers that I don't look at anymore because I just don't understand the meaning of their uncertainties. And they pretty much find Kilanovas every week. So something is certainly not correct, right?
Thanks. So all of our models are biased, and we sometimes try to correct the bias and overcorrect that. Yesterday, all comments were from this side, and we had to encourage people from this side to do that. Now we have had all comments from here. So let's see one comment from here. Okay, Mansi, and then Matthew. We'll come back to you, Matthew.
So I just have a question on the similarity watch list that Kostya brought up. So does anybody have a tool where you could give it a light curve, right? And say, just based on the light curve and color evolution, give me the closest matches in the entire ZTF or whatever database, right? Rubin, the entire world database, so that I can actually do rates on how unique something actually is. It doesn't sound that difficult. I mean, I hope somebody's done it, but like done it well enough that it takes into account weather gaps and the fact that there are missing points in the data, and you're looking for similarity, not identical, right? I mean, close enough in.
So in ZTF itself, we have done it a little bit for TDs. And once you start going into the noise, you start seeing all kinds of things. That is where, again, what is the next possible classification you can do based on real observation is what comes in. But yes, that is exactly what we need to do. More templates and getting into the weeds, really.
So, I mean, there's 2 aspects. One is go back in time and tell me everything that's similar. The other is next time something starts to look like it, tell me, okay, this is like your, favorite car. Yeah. So that's what I wanted to know a little bit more about, like how evolved or advanced is this at this point? That was the question.
Yeah. Matthew?
So actually, I wanted to just touch back on this uncertainties of classification. One of the problems is the interpretation by the average astronomer about what you mean on uncertainty and classification, and how do I propagate that through my system? If you say, "Oh, this is I'm 3 sigma certain that this is a type 2b supernova," what does that mean? Does that mean that 90% or 95% of the time it's always going to be a type 2? But if you give me 100, that the problem, boils down to, and I'm not going to say frequentist versus Bayesian, but there is an interpretation problem fundamentally. And if you say to someone, I mean, if I tell you it's going to rain, there's a 50% chance it's going to rain tomorrow. There's a slew of opinion on that. And if I say there's a 50% chance that this is a kilonova, there's a slew. And so we need to solve that problem as well. We need to tell the astronomers how to interpret the uncertainties we're propagating on classifications, as well as actually having a calibrated method of doing so.
Absolutely. So more training for astronomers as well, rather than relying on some of the LLM-based things that we may be getting. Ryan, how much time do we have? We can continue for a few more minutes. Okay. Yes, nice.
One of the things we have been discussing in the brokers is whether we should put calibration plots on all of our classifiers. So people, when they do a cut on a probability, provided they know what is actually the calibrated probability, like how many true objects they have. And this is a practice that maybe we should implement, all of us. Not trivial if you're retraining your model all the time, so you need to update them, but yeah.
Yeah. So generalization is something that we should be looking at also, and calibration will tell us more. So the example that Kostya had about the green square, that was great. But right, if the highest probability, highest confidence you have is 6%, that already tells you that maybe it's not getting it right, right? It could be anything in principle. And so when people train their methodologies on a single data set or one survey, it's always good to look at something else, how it would predict on that, what it will say on that, and so on. Making sure that we give all kinds of possible inputs, maybe even non-astronomical inputs, how they work. Okay, any final thoughts? Any other question that has not been touched upon here? So what are the things that we'll laugh at 5 years from now, 5.5 years from now? So there were some thoughts yesterday that ML is dead, only AI works, and then we get a lot of hallucinations also. So how does that work in? So where is all this going in? Will everything be agentic, for instance, or is that something? Okay, maybe we can discuss that over coffee. Let's break off for coffee. Thanks to all the speakers today.